Okay, so this is the 14th lecture. So, what we're going to talk about today is a combination of two previous lectures. We're going to combine the lecture on continuous random variables with the lecture on joint discrete random variables in order to build a concept of joint continuous random variables. So, joint continuous random variables represent the idea of a list of random real numbers or a random point in Euclidean space. So, the correspondence between lists of real numbers and points in space is fundamental to every aspect of math. It's usually referred to as Cartesian coordinates, and the dimension of the space where your point lives is the length of the list of real numbers you're considering. So if you have two continuous random variables, that represents a pair of random real numbers, or equivalently a random point in the plane. If you have three continuous random variables, that represents the idea of a random triple of real numbers, or equivalently a random point in three-dimensional space. So we have these three equivalent formulations for how to define discrete random variables, and we found that there were three equivalent formulations also for defining multiple discrete random variables. We had the idea of a family of measurement functions from the sample space to the real numbers. So this is the foundation of how to think about random variables, and it's what provides the theoretical connection to the axioms of probability. And we want to think of this physically as representing a collection of measurements about a system where the sample space is now, or the sample space is some kind of physical object that we're observing, and the random variables are certain numerical parameters that we're taking into account. So with multiple continuous random variables, it's exactly the same idea, except now instead of thinking of your random variables as having only finitely many possible values, you allow your random variables to be arbitrary real numbers that could vary continuously. And this is supposed to represent the jump from something like two fair die, where you're rolling 1 through 6 on the first die and 1 through 6 on the second die. That's two discrete random variables, whereas two continuous random variables would be like, I have a point on one stick, and then I have a point on another stick. stick. And we could think that these two sticks have length 1, and they're moving around in time, or we're sampling at various timestamps from points on each of these sticks. So we have some kind of random law, which is telling us a point on, let's say I have a wooden stick and I have a metal stick. And so I have some kind of random law, which is giving me the distribution of a point on the wooden stick and a point on the metal stick. And I have a certain probability of finding any particular pair of points that represents the joint distribution of these two measurements, where I'm looking at a point on one stick and a point on another stick. Another physical analogy you could consider would be just to take one of the discrete examples we talked about before with measuring color and intensity of a light bulb, and to say, well, actually, it's a little bit artificial to even think of that as a discrete random variable in the first place. Normally, if a physicist is measuring color and intensity of a light source, they're going to think that these parameters could vary continuously. They could be any particular real number, and, they would measure it to as much precision as your optical device can record, with the intuitive understanding that having a very precise optical device is approximating the underlying reality, where these parameters, color and intensity, are taking values that could be changing continuously. So the most important way to think about multiple continuous random variables is what I have highlighted in teal. So we had a concept of a probability mass function for multiple discrete random variables, where we had a list of possible values, and when we input a list of possible values, we get the probability that the sequence of random variables simultaneously achieves that list of values. So instead of probability mass functions, where you input possible values of the random variables, for multiple continuous random variables, what you do is you have a probability density function defined on a Euclidean space whose dimension agrees with the length of the list of random variables. And what you can do with this probability density is you can give yourself a list of lower bounds and a list of upper bounds. So here I've described the lower bounds as A1 through AN, and I've described the upper bounds as B1 through BN. And the question I'm asking is, what's the probability that my first random variable falls between the first lower bound and the first upper bound, while the second random variable simultaneously falls between the second lower bound and the second upper bound? and I'm putting all of these conditions, and my last condition says that simultaneously with all the previous ones, my nth random variable satisfies the nth lower bound and the nth upper bound. So I have an event in my probability space which is defined by my list of random variables simultaneously satisfying a list of lower bounds and a list of upper bounds. So ultimately what we're doing is we're defining an event in the probability space and calculating its probability, just like the axioms are designed to do. But what this event is calculated as is you do a multiple integral over all of these upper and lower bounds of the probability density function, which is a function of n variables. So I have this function of n variables, which is the probability density, and I integrate it where the bounds of the multiple integral are the list of lower and upper bounds that I chose when I was asking the question about simultaneous satisfaction by my list of random variables. So if you can see here why lists of 2 or 3 random variables are much easier to work with conceptually than lists of 4 or more random variables, because if you've taken multivariable calculus, you probably concentrated on calculus in 2 and 3 dimensions, whereas calculus in arbitrary dimensions is usually done in a higher level course, which would be a third course about calculus. But you can think about the case of a list of 2 random variables or a list of 3 random variables and sort of trust me that in this course I'll only ever ask you questions about lists of 2 or 3 random variables. So I won't ever ask you a question about 4 continuous random variables, because that would require doing 4-dimensional calculus, which is something that I don't really expect students in this course to have a background in. But I'll ask about lists of 2 and 3 random variables, which correspond to calculus in 2 dimensions or 3 dimensions, with functions of 2 random variables telling me the probability that a pair of, with functions of 2 variables in the probability density telling me the probability that a pair of random variables simultaneously satisfies a pair of lower bounds and a pair of upper bounds. So if I want to think that n equals 2, I could just call these things x and y. And I could ask for the probability that x is between a1 and b1 and y is between a2 and b2. And in that case, I would have a double integral from a1 to b1 and from a2 to b2 of qxy, s1, s2, ds2, ds1. So I would have an integral of 2 variables. I could even simplify things further by calling them s and t. So I could think that for a pair of random variables, I'll sort of simplify all of this notation. I'll say that I'll call the random variables x and y. I'll call the lower bounds A, B for X and C and D for Y. I'll call the inputs to the probability density S and T, and everything will simplify to a double integral rather than a n-dimensional integral. Okay, and then the concept of a cumulative distribution function is literally identical to the concept of a cumulative distribution function for a discrete random variable. For multiple continuous random variables, the cumulative distribution function is very closely related to the probability distribution density just by setting all of the lower bounds to minus infinity. Okay, so let's have a look at an example of a pair of continuous random variables. So we can think that we have a sample space with the unit square. So a square of side length 1. And we can think that what we're doing with this random variable is picking a random point in a square. So the one-dimensional standard uniform distribution was picking a random point on a stick of length 1. We can think that maybe we have like a table with side length 1 in the shape of a square, and we're picking a random point on the surface of this table. So in terms of an explicit physical experiment, you can think that one-dimensional standard uniform is I have a stick and I'm throwing a dart at the stick with no control over where it lands. And so you can think for the two-dimensional standard uniform, I'm like dropping a coin on the surface of a table or something, and I know it's always going to fall somewhere on the table, but I have no control over where it lands. So in that case, the two random variables are the x coordinate of where your coin landed and the y coordinate of where your coin landed. So I'm dropping this coin on a table, which is square with side length 1, and the two numbers I'm measuring are the x coordinate of where it landed and the y coordinate of where I landed, given that I've chosen a particular vertex of the table to serve as 0, 0, and another vertex to serve as 0, 1, and another vertex for 1, 0, and the final vertex would represent 1, 1. So once I've chosen this labeling of the vertexes of the surface of my table by the vertexes of the square, I can think of dropping an object on the table with no control over where it lands as giving me a pair of random numbers for the two coordinates of where it landed. And in that context, what I mean when I say I have no control over where it lands on the surface of this table is that probability is equal to area. So if I want to know the probability that my coin lands in some region on the table, the probability is just the area of that region where I think of the whole table as having area 1. Okay, so you can see on the right in red, I have a picture of the probability density function for the standard uniform distribution. And, the probability density for the one-dimensional standard uniform looked like a step function of height 1, which kind of looks like a stick. And I have this two-dimensional step function of height 1 over the unit square in the plane. And it kind of looks like a table, which suggests the physical experiment I was trying to use to motivate this. And so what we can think of is that if I have some region in the plane and I want to know the probability that my coin lands on top of that region. So I have a table which I think of as side length 1, and I assume that my coin is going to land on the table. And then I think of all of the rest of the floor as this rest of the plane, and I say that my coin is landing uniformly on the surface of the table, and it has 0 chance of landing on the floor off of the table. And so that's how you get the picture I've drawn for the two-dimensional standard uniform distribution. Okay, so if we think of x as a single random variable, what happens is we get a copy of the one-dimensional uniform distribution. And if I think of y as a single random variable, I get another copy of the one-dimensional uniform distribution. So the two-dimensional uniform distribution can be thought as a certain kind of coupling between a pair of one-dimensional uniform distributions. And you can see that I have this calculation on the lower left where I say, okay, what's the probability that a random point in my square falls between A and B and C and D? So the way you want to think about this is I have this kind of infinite floor which is going off in a plane, and then I'm standing at my table and dropping the coin, and the coin is certain to land on the surface of the table, but I have no control over where it lands on the table. And then what this probability asks is it takes the coordinate system I specified by choosing vertexes on my table and picks any kind of rectangle on the infinite floor. And it says, well, if I measure this rectangle on the infinite floor, which may or may not be underneath the table, what's the probability the coin falls above this rectangle? So I have a coordinate system on my infinite floor, which is determined by my choice of vertexes on my table. And then I draw some rectangle on the infinite floor, and I assign numbers to the vertexes of that rectangle according to the table-based coordinate system. And so if the one side of that rectangle I drew on the floor has length from A to B, and the other side goes from C to D, what I get in the integral defining the probability is an integral of the one-dimensional uniform from A to B times an integral of the one-dimensional uniform from C to D. So I'm just overlapping the rectangle I drew on the floor with the surface of the table, and I'm calculating the area of the subrectangle that falls from intersecting the shadow of the table with the rectangle on the floor that I'm trying to analyze the probability of. Okay, and so you can see on the lower right, I have the cumulative distribution function of the two-dimensional standard uniform distribution. So what this function looks like is it's 0 if the upper bound is too small to fall under the shadow of my tables. So what this cumulative distribution function does is it says, instead of just looking at a rectangle on the infinite floor, I'm going to pick a point on the infinite floor and look at the sector that goes off to minus infinity according to the coordinate system based on my table. So if I pick any point on the infinite floor, my table-based coordinate system tells me a quadrant of the floor which goes to minus infinity in both directions. So I pick a point on my infinite floor, I choose the quadrant that goes to minus infinity in both directions, and I check what's the overlap between that quadrant and the shadow of the table. And then I say, okay, so the overlap between that quadrant and the shadow of the table is the probability that when I drop my coin, it's going to fall on top of the quadrant. Okay. So we can have a look at an example of the two-dimensional general uniform distribution. So I got the two-dimensional standard uniform distribution by coupling two copies of the one-dimensional standard uniform. And I'm going to do the same thing. I'm going to couple two copies of the general uniform or distribution to produce a two-dimensional general uniform. So what the idea of the two-dimensional general uniform distribution is, you can think of the same experiment where I'm dropping a coin on the surface of a table with no control over where it lands. But now my table is not a square with side length 1. It's a rectangular shape with some other side length. So, you know, the way mathematical generalizations work is everything I'm saying about this arbitrary table also works for the square table, but it doesn't necessarily have to be square anymore. So I have this rectangle, which might not be a square, and I want to think about the probability that my coin falls on some region of that table. And what I'm going to do is I'm going to, again, say that probability is proportional to area, but I need to include a constant of proportionality in order to satisfy the axiom of certainty. Because since I'm not hypothesizing that my table has area 1, I need to rescale the area when I calculate probabilities so that the axiom of certainty is satisfied. And this normalization factor multiplying the area is just the total area of my table. So I have the formula for the area of a rectangle, just the product of the two side lengths, and I'm dividing area by that normalization factor in order to satisfy the axiom of certainty when calculating the probability that my coin falls on a certain region of the table. And I also again have these two random numbers, which are the x-coordinate of where my coin lands and the y-coordinate of where my coin lands. And I can think about the probability density function, which is not quite the same physical picture as before, because it's not exactly a copy of my table. It's a shorter copy of my table, or maybe a taller copy of my table. It's a copy of my table whose height has been rescaled so that it matches the 1 divided by the area. So in order to, again, this is all because I need to satisfy the axiom of certainty, which is telling me when I go from the physical experiment to the mathematical abstraction of the probability density, I need to leave the precise detail of the height of my table in reality behind, and I need to assume that the height of the probability density is 1 divided by the area of the table. Okay, and so then I can go about calculating the integrals for the probability density in the same way as I did for the two-dimensional uniform. I can say, well, I'm going to draw this rectangle on my infinite floor, and I'm going to calculate the area of the overlap with the shadow of the table, and then I'm going to divide by the area of the table. And what that ends up doing is being equivalent to integrating the general normal alpha beta from, so I have, if alpha and beta are the limits of one side of my table, I need to use the general normal in one dimension with parameters alpha beta and integrate that over the bounds I'm interested in. And if the other side of the table is gamma delta, I need to use the one-dimensional general normal with, or the one-dimensional general uniform with gamma delta, and integrate that from C to D. So the explicit way this works out in calculus is that I have a product of two integrals of one-dimensional general uniform distributions, and I calculate those integrals of one-dimensional general uniform distributions in the same way as I did in the lecture on that topic, and we come out to get this product of intersecting side lengths. So minimum of beta b minus maximum of a alpha is the length of one side of my rectangle on the floor intersected with one side of the table. And minimum d delta minus maximum c gamma is the length of the other side of the table intersected with my rectangle on the floor. Okay, and then we can see the cumulative distribution function is just the same as the cumulative distribution function for the two-dimensional standard uniform, just rescaled appropriately. Okay, so now let's have a look at the two-dimensional standard normal distribution. So again, as with the one-dimensional normals, there isn't usually an explicit measurement associated with the normals like there is with the uniforms, at least in terms of a physical experiment. The two-dimensional standard normal arises as a large-scale limit of random events, just like the one-dimensional standard normal. So the way the two-dimensional standard normal gets introduced into math is that you imagine you're in one of these coin flipping theaters that served as the basis for our discussion of the de Moivre-Laplace theorem. And there's two adjacent holes, and in each hole there's a game with a fair coin going on. And what you're doing with a two-dimensional standard normal is you're approximating the long-term result of the pair of games. So the random number in the first case is the result of the game in the left hole, and the random number in the second case is the result of the game in the right hole. And what you're tracking over time is an appropriately rescaled version of this pair of random numbers, which are giving you the results of these two games. And there's a higher dimensional version of the de Moivre-Laplace theorem, which tells you that if you track the long-term result of a pair of fair coin games and rescale everything appropriately, it converges to this curve, which is literally like a bell rather than a one-dimensional projection of a bell, as with the thing usually called the bell curve. So the bivariate bell curve or bivariate Gaussian is this shape in three-dimensional space, which is the graph of a function defined on the plane. And the surface defined by this graph of a function on the plane looks exactly like a real-world bell. And it's what you get by taking a copy of the one-dimensional standard normal and rotating it around. So I can produce the two-dimensional standard normal by thinking of drawing a one-dimensional standard normal above the x-axis and then pinning it at the peak, which is above the origin, and then spinning it around that pin at the peak. And when I spin it around like that, what's going to happen is that I'm going to get this shape, which is like a two-dimensional bell sitting over a plane in three-dimensional space. And so the height of the two-dimensional standard normal is 1 divided by 2 pi. So There's a dimensionality constant, which is 1 divided by 2 pi to the dimension over 2. So in one dimension, I have the exponent on 2 pi as a half. In 2 dimensions, I have the exponent on 2 pi as 1. If I had a 3-dimensional standard normal, I would have the exponent on 2 pi as 3 over 2. The 3-dimensional standard normal is, again, beyond the limits of the human eye to visualize as an explicit graph, because it's a graph of a function defined on 3-dimensional space, which goes up into the 4th dimension. But the 3-dimensional standard normals and the higher dimensional standard normals all follow this basic picture where they look like 1-dimensional normals rotated around an axis that fixes the peak. Or what you would do in 3-dimensional space is you would draw a 1-dimensional normal over an axis, and then you would fix the peak, and then you would find that because you're in 4 dimensions, if you fix an axis, there are 2 independent rotations, and you would have an axis that fixes the peak, and then you would rotate it in the 2 independent dimensions, which are going to fill out 4-dimensional space. So we have this two-dimensional standard normal, which is a surface in 3D space obtained by rotating the 1-dimensional normal around an axis fixing the peak, and higher dimensional normals are obviously harder to visualize, but the basic idea is that they concentrate at the origin and decay symmetrically and exponentially as you move away from the origin. Okay, and so the pair of random variables where we're looking at the long-term result of the game in the left theater is X, and the long-term result of the game in the right theater is Y. Those random variables are both distributed like standard normals because they're individually fair coin games. And we can deduce the 2 copies of the 1-dimensional standard normal by integrating the 2-dimensional standard normal over the orthogonal axis. So one copy is q sub x given by integrating over the t-axis, and the other copy is q sub y given by integrating over the s-axis. And the point is I can figure out the probability that my pair of numbers satisfies a pair of upper and lower bounds by integrating this 2-dimensional standard normal over a rectangle. So if I say, all right, what's the result that the heads player wins by 35 in the left theater and the tails player loses in the right theater? And then I can do the De Moivre-Laplace theorem and calculate the 2 individual probabilities and say that the 2-dimensional standard normal will give me the product of the probabilities. Okay. So the last example we're going to discuss is the two-dimensional general normal distribution. So the two-dimensional general normal distribution has 5 parameters, which are telling us lots of details about our pair of random numbers. So we have the mean of x, which will write mu x, and that's the bias of the coin in the left theater. And then we have mu y, which is the mean of y, which is the bias of the coin in the right theater. And then we have the standard deviation of the left theater coin and the standard deviation of the right theater coin. So those 4 parameters are more or less what you'd expect from a naive coupling of 2 one-dimensional general normals. Each one-dimensional general normal is parametrized by a mean and a standard deviation. So these first 4 parameters are what I need to specify a pair of general normals individually. But this is really where things start to get subtle, because it turns out that you also need an additional parameter, which is the cross correlation between these 2 random variables. So the situation here would be that maybe the heads player and the left theater and the heads player in the right theater are somehow coordinating their activities in order to manipulate the betting markets which are going on outside. And so if the heads player in the left theater and right theater are somehow coordinating their activities, then it's no longer valid to model the game as just 2 copies of general normals in one dimension that have nothing to do with each other. If the heads players are coordinating their activities, then you might have this extra parameter called the cross correlation, which comes into defining the two-dimensional random law that describes the pair of results of their games. So the cross correlation is always a number greater than or equal to 0 and less than 1. And the way to standardize the two-dimensional general normal is to standardize each of the individual copies by setting both means to 0 and both standard deviations to 1. And then the appropriate standardization of the cross correlation is 0, which says that actually the heads players are not coordinating their activities at all. And so the heads players, well, well, when I say, let me clarify a little bit. When I say the heads players are coordinating their activities, a better way of saying that would be to say that instead of flipping coins, what's happening is random numbers are showing up on a pair of TVs. So there's a TV in the left room and a TV in the right room, and random numbers are showing up on the left TV and showing up on the right TV, and people are betting on them in the same way I was describing before. So the metaphor you need for cross-correlation is maybe moving a little bit away from the explicit coin flipping game, but you can still have this idea of a theater where people are betting on random numbers. And the point of the cross-correlation would be that there's a TV in the left theater, which is showing the results of a coin flipping game, and there's a TV in the right theater which is showing the results of another coin flipping game. But there's some sort of secret subterfuge going on where these two TVs are not actually showing the real numbers. They're somehow being coordinated by some person trying to manipulate the betting markets so that they're not independent of each other. Okay. And then you have this formula at the bottom of the page, which is the probability density function of the two-dimensional general normal. I'll just say that the thing 1 divided by what you have in the beginning is necessary to make the integral of the whole thing 1. The exponent is what's called a normalized quadratic form. It's, in fact, a positive definite quadratic form. That's how theoretical mathematicians understand it. But what you'll need to do with this formula is plug in specific numbers and not actually deal with it in any context where you have to use variables. So you'll never have to work with this formula in the complexity it's written. The worst thing that will